asking someone preparing his PhD in artificial intelligence. He make an article by AI and publish it with to remember it, please. With high-level institutions, and after that he asked them to forgive him because he make this thing. The first sample from IE University in Spain. The second was Google Brain and DeepMind and Job Hopping's University. After they attribute the article, they accept it and publish it. After that, he smiles and he is happy because they publish the article, which authored by computers, by artificial intelligence. So he take this case, asking authors to make fraud, academic fraud, and publishing to distinguish between good articles and bad articles. So it's a very good sound, good sound, not appear, and also many of levels in the academic levels are making that like this. So it's in Arabic, and I wish to translate it to English and giving you as a copy, inshallah. Sorry for interrupting.
No, so sure, Dr. Samer. I want to give a small introduction about it. Dr. Samer, he is publishing on monthly basis a full journal related to the Islamic finance and finance around the world. Now, this article is in the last issue. It is published in the last issue. I will work on translating it. But after 1st of June. This is the only thing. Tom, welcome back. By the way, we are live on YouTube, so we can start.
Very good. I will share my screen. Let me get to my important screen. Here we go. Okay. How is everybody? Good. There we go. Excellent. And then I think I better move this chat away. Okay. Okay, missing values. We don't want them to ever leave, so we're inviting them back. How do we get them back? Very carefully. So why do we care? Because our predictions will suffer, and they'll suffer in unknown ways. That's the key. That for every data point that goes missing, we don't know how big of an effect that will have. And the missing values is one of the largest challenges to accurate analytical work. So we've got to find the most effective methods to deal with missing values and learn which methods are most appropriate. And we did, of course, last week, show one way to deal with missing values. I'm going to ask y'all to forgive me. As we're writing the book, sometimes these lectures come out a little non-linear, but part of it's okay because the process itself can be very acyclic. And as we keep going through, you'll get a better sense of that. So, I'm a big fan of fake data, but why does fake data help us understand how to better deal with missing values? Well, as you know, it grows insights, because if we're producing the data with the model and we're modeling, then we should be able to repredict what we produced. And we can look at that fake data with and without noise. We can add different types of noise. So all of that helps. Excuse me a minute. But we have to, if we change which data is missing and the amount that's missing with the fake data, we can gain even more insights. Now, how does this help us? Well, if we're looking, if we're just trying to understand how we're handling missing values, now we can know the exact effect it's having. Whereas for real data that's missing, we don't necessarily know what the effect would have been. So now we get to study it directly with, in other words, we're not blind. When we're working with real data that has missing data, we're blind. We're doing the best thing we can. But to gain more insights, if we use the fake data, we can see the effect because we made the data go missing where and in how much that we wanted to. So again, skills with fake data are so helpful. And this is a new English word, muchji. I know it's not very common, but trust me, it's a real word. And I would never present a typo on YouTube. So again, though, the fake data is not the real data. We're just learning it to help us improve our understanding of how to more effectively deal with missing values. Oh, I can't stand it. This is how anal I am, guys. I can't believe I did that. Okay. Don't be as anal as Tom. Okay, reminder. Now, just like we have mathematical mechanisms to do machine learning development, there are mechanisms that affect missing data. And these mechanisms determine the probabilities of data going missing. Ivy says hi. So understanding them means understand how to deal with missing values. But there can be limits to that understanding, unfortunately. So the first characteristic, the first mechanism of data going missing is missing completely at random. And let me change something real quick. Okay, good. Y'all feel free to ask me questions in the chat too, if you want. So missing completely at random. This just means if it's missing from a sample, it will go missing the same way from the entire population. Now, if we're going to have some type of missing value, this is our preference. In a way, I'll explain why I mean in a way, but it's not, I shouldn't say super rare. Y'all have to watch me. I get hyper dramatic. It's rare. It's more rare than the other kinds. The next kind is missing at random. And this is actually data going missing for understandable reasons. So I feel it's a bit of a misnomer, but they just mean the people that come up with this. It's the best effort to say, okay, we know why it goes missing, but it can happen at random. And so, but it's not really randomly missing. This phenomenon can happen at random. So people, for example, an example of this, people with high IQ might be less likely to state their salary, so they just don't fill in the survey data. This would be an example of this. Depressed males are less likely to answer depression questions. Now, I didn't make these up. These are very common examples out there in the literature because they're easier to understand. And then it is impossible to statistically verify missing at random, but we can usually make some reasonable assumptions about it to help. For example, if we talk to domain experts in these two different fields, they can help us understand why this happens. And then we can try to adjust surveys or maybe do face-to-face interviews to gain greater understanding to intelligently adjust the missing values. Now, there's missing not at random. And this is data that doesn't fall into the other two, but it's missing due to the nature of the value itself. For example, sometimes high IQ people have so much income and from so many different sources that they don't even know their income at any given moment. It may be going up and down due to the income streams, the different ones. And depressed people can be so depressed, they're not even able to complete the survey. So this is where you have to take more action or fill in the blanks with domain experts. But even then, you have to be very careful. So all of this takes great care. And so understanding which mechanism of missing data you're working with can be very helpful in these regards. Remember, when we identify that we have missing data, we want to deal with it at the source, but then also with this data that we have in hand. So we may have to go back and talk. We were just talking about this in Tech Time Chat. Every step in our machine learning process is a chance to get out of our chairs and go have a talk with someone. You know, when we're collecting this data, we're getting missing values for this. Is there a way we can work together to have less missing values here? But then we go back to the data set. Okay, I've got this data. It's still valuable. How can I deal with the missing value? But don't be one of those data scientists that sits in their chair all the time and doesn't get up out of their chair and go deal with the missing data at its source, or go deal with the other data problem at its source. Have a spirit of going to talk to others that control the data influx and get that data influx cleaner and more complete. But once we know what type it is, what mechanism is causing the missingness, we can prioritize knowing how to mitigate those missing values, like I was saying, at their source. But for the remaining data, we can also choose methods thoughtfully now, because many of the methods rely on it being MCAR. But if it's not MCAR, you got to deal with it differently, as we discussed. So why do we even care? Well, during exploratory data analysis, if we have missing values, we can't really do some of the early analysis we need to do. And what's some of the earliest analysis we do? It's correlation. And why do we do correlation? We're looking for collinearity, but also feature strength. If we see that a certain feature, by the way, at first it's just the data. How do we get a clue about which data is going to become features and which data is going to become labels? We get out of our chair and we go talk to our organizational leaders and our domain experts and say, what do we most care about? Now, hopefully you've already had these conversations, but based on your learning from them, you can begin to have a clue what data needs to become what. But one day, or for one pipeline development, you may be working with this group of features and these labels, and then in another pipeline development, those may be completely different, of course. It's not always going to be the same. So during that exploration, we're seeing, well, if I see a high correlation between this data type, this variable type, and this variable type, it could very well be that this will become a feature and that will become a label, but it could be the flip-flop of that too. So it's the spirit of you have to get out of your chair and go talk to the organizational leaders and the domain experts. But as you're doing that exploration, these missing values can really affect what you learn from that analysis. And so that's why we care so much about them. And one thing we do early on is a correlation, like I'm saying. Now, as we narrow down, we use correlation strength to also find collinearity. That's just saying, hey, as far as the model's concerned, these two features are playing the same way. Now, as we keep going, you'll discover PCA can almost always decouple these, make them look independent of one another. because of the way it changes the space perspective. But also we use tools to either eliminate one of those variables, or if we're using something down the decision tree path, let's remember, on this side of the house, we have linear regression. That's the building block to logistic regression. That's the building block to neural networks. That's the building block, the beginning of convolutional neural networks and transformers. On this side of the house, though, we have things like decision trees, random forests, boost methods, and then we can mix them all with ensemble methods. So, but the beginning of all of that is, in getting the right set of data, is just looking at good old correlations. And I hope you've been reading these slides some, but that I was speaking to what's on this slide. Any questions at this point before I move on? Because I want to make sure there's no confusion before I go on.
I do have a question, if it's possible.
Yes, yes, Amar.
So we are talking about EDA as in our error assessment method, our error assessment methodology for data. But in the same time, does it always, is it always able to detect our problems? In other words, I'm saying that maybe we have two data that concludes the same feature. And in this way, PCA would differentiate them, but they would be totally useless to have both of them.
So it's interesting, Amar, where I was going with that. I should have clarified something. The reason I was talking about, and by the way, just to be clear, EDA is exploratory data analysis. So we're exploring all sorts of things, but I was trying to do, I failed to completely finish my point, Amar. So I'm glad you asked this question. Let me see if this will help. When you go down the linear regression path, which is linear regression, logistic regression, neural networks, etc., that's where you really care about this stuff, getting rid of collinearity and reducing dimensionality. When you go down the decision tree path, oh, and one exception to that rule is when you do introduce PCA. I was asking the tech time chat people, if you find a case where the collinear features or variables are not decoupled and made independent from one another with PCA, with going to eigenspace, please show it to me. But I've never seen one, because that's what eigenspace, eigenanalysis is very good at. But over on the decision tree, random forest, all of that, that doesn't really care about scaling or collinearity or any of that. It's very robust that way. So, but yet it's still very valuable to know. Even like I have this one friend, she's a brilliant data scientist, but she said, Tom, the place I'm working at is so boring because we always use random forest. And random forest is very powerful for the type of analysis they're doing. And they have a lot of data now, so I could imagine that being true. But in that realm, it precludes the need to scale your features and get rid of collinearity. It can deal with all of that somewhat like PCA can, not in the same ways, but still reducing dimensionality, understanding what features are related to one another through correlation, all of that's still valuable as we're exploring the data and doing analysis with it. Now, Amar, I'm not sure if I answered your question, so let me know if that helped a little bit at least.
No, you actually did very well. That was my exact point, that yeah, PCA in this situation and in most of the situation is able to detect, like to differentiate the features that are correlated, but you can see the difference between them. Even if they are correlated, they might have other explanations and need on the like inference level.
Exactly. And I have a suspicion, I still think I would, because of the nature of neural networks, I would tend to prefer to still scale my features before I feed them into a neural network. And I would still prefer to reduce my variables using linear regression and lasso before I go into a neural network, or logistic regression and lasso, depending on whether I'm doing regression or classification. But the spirit is reducing the dimensionality of the problem. But my guess is that neural networks could also handle collinearity pretty well. They just say, oh, what it would train the weights in the connections to say, yeah, you don't need that too strong here, because you got two players doing the same thing. Well, if we move on, so how do we calculate correlation between two variables? And this is where I'm a blessing and a curse to you guys. You got to remember, I'm a classically trained mechanical engineer. And even in my math classes, they insisted that we knew how to derive things from scratch. And back then, we didn't carry laptops in our backpacks. I carried very heavy engineering books, and I'd go to a computer lab where I was on a terminal to connect to a giant computer when I was using computers, but we weren't using them as often as we do now. And so we had a real emphasis on understanding how to derive equations from scratch and then use them and understand the terms themselves, because we couldn't always afford the computations. So we were looking very carefully at the equations to understand things. Well, I still find that extremely valuable, and I'm going to hopefully talk all of you into doing the same. So this is Pearson's correlation coefficient equation. This is how you calculate it. And I want to encourage y'all, I'm going to give a couple of assignments, but they're going to be completely voluntary, and I hope I get volunteers. There's also Spearman's, and there's, I forget how to pronounce it. I should have just put them in the presentation, but something Tau. But there's three major ones that are pretty popular. I think Pearson's is the most popular because it tends to be the most robust. But let's go through this. Here's the coefficient we want to calculate for the degree of correlation between two variables, only two, X and Y. So the first thing is we take the products of X and Y and we sum them up and we multiply those by the number of samples. And we subtract from that the summation of X and the summation of Y as a product. Then in the denominator, we're looking at N times the summation of the squares of X minus the summation of X squared. And then, excuse me, the same sort of thing with the Y, we multiply those together and we take the square root. Now, you'll recognize this as somewhat of a variance study on the bottom and somewhat of an average study on the top. And why is that important? It's basically saying, the way I see this equation, it's looking for the degree of interaction here minus the degree of separateness multiplied together, and then dividing by the variance. So if the variances are very low, or things that focus on the variance, I should say. If the variance is very low and the interaction is very high, you'll see a high correlation factor, right? So let's see what this looks like. If we take, this is the mechanics of this equation. We've got X, we've got Y, and what are the other things we need? We need X times Y, we need X squared, and we need Y squared. But we can also take, as we see, we need the sums of X right here, the sums of Y right here, Now we can take the sum of the interactions right here. Then we need the x squareds, yes. We already have the sum of x, and then we can just square that. We have the number of samples is 6, which is the last number here. I should have pointed that out earlier. We have our y squareds, and then we have our summation of y that is squared. This example in excruciating detail, and I mean that in the fondest way, is here. And of course, I'll make these slides available to you guys by link or by download to our repository. Now, the assignment I want to encourage you guys to take is this. Code this up in Python. Make sure you can send in any 2 variables. Then take the effort to go learn Spearman and find the more general form of Spearman. Now, Spearman depends on rank order, but there's a more general form of Spearman that you don't have to worry too much about how you deal with rank order. But so Jonathan, because you're becoming advanced very quickly in Yogita, I would challenge you two to do the Spearman. And maybe do both, but the Spearman's going to be perhaps a little harder because I haven't lectured on it and you're going to have to go learn it yourself. But I think you will enjoy the exercise. Now, these will not be super hard assignments, just so you know, but they will be very valuable in my opinion. So, and then some brave soul, well, maybe I'll go do the that third one, and I'll put in, oh, Geith will take it. Well, Geith, aren't you writing a book? Do you have time?
Because I'm writing the book, I would have time.
Oh, perfect. Yeah, it would be good to put it in the book. That's true. Okay. And by the way, I'm finding when I have these kind of questions, I love this site. Statistics How To, they're great, guys. Okay, now you've seen this before. I've even heard, when I've read a lot of material on these, it is confusing when they talk about pairwise deletion, but let's talk about rows. When you're doing this correlation analysis, this is early in our EDA process. Correlation is probably the earliest analysis you'll do. A lot of the mentality is, okay, we'll just delete the rows that have any missing values because we can't use those in all of the correlation analysis. And I'm like, what? I don't think that if you do dataframe.corr, like when you're using pandas, I would like to verify this and it would take some experimentation to figure it out. But I think when pandas is running through that, they're probably doing pairwise deletion always, but I don't know. But this deleting the rows listwise is, in other words, each list, when it has a missing value, that's a travesty. Because it's not necessary for your analysis. Now, we've already talked last week about columns that have too many values missing. If we have no hope of predicting those missing values in that column, might as well delete that column. That is an even bigger travesty, but a more necessary one than the deleting all the rows that have anything missing. Pairwise deletion is saying, okay, I'm going to look at the correlation between variable 1 and 2 right now, and I will only delete from my analysis those rows that have missing values for either variable 1 or 2. But I'm only looking, in other words, take those two variables, separate them off, and now you do, yes, you do delete the rows in that segregated set. In other words, if any, but you You will delete fewer rows that way and have more data for your correlation analysis. Now that is really hard to explain, even though it's simple. I'm just realizing now I should have made a graphic for it. Does that make sense to everyone? Let me know if it does not.
It actually does. Yeah, it's pretty simple, right?
Okay, good. And if it doesn't, guys, please just let me know how. Oh shoot, I was going to read. I'm not an SLD speaker. I do not see where my rename thing. There it is. Okay, good. Now, guys, the hero of today will be someone that says, "No, it's still not clear to me." Well, I'm going to say it one more time, just in case.
Let me explain it myself.
Yes,
and
perfect.
Like you can. Okay, so deleting an entire row would make us lose a ton of feature if it exists. Okay, so our substitute solution here is to compare a two features together, and then we will this would be extendable to other features. So we would take only two features, take them out, apply the method that we were talking about, the
row deletion.
Pearson,
now we
Pearson correlation maybe on them.
Yeah. Go on ahead.
Okay, apply Pearson correlation, but while deleting only rows where one of each feature is missing. So this way we would have more rows next, like and other features to differentiate between.
Exactly, Amar. And I find that even though it's a very simple principle, it for some reason it's hard to explain. And I even found someone begging for a toy example of this on one Stack Exchange site. But it literally, it really is deletion of rows. That is, if you take those two features, isolate them, now call that your data set. Now you delete every row with any missing value because you're only looking at the two. You will end up with more than if you delete all the rows with any missing value. So thank you, Amar. Good explanation. I think between the two of us, they got it. Now, this is why this is so important. We to do the correlation, we can't do the correlation with missing values, but we're being very judicious about how we delete the values, and pairwise is the most careful form. With the imputation, it's a subtle point. If you guys, and by the way, I apologize in advance when we're talking through machine learning development, because it's so acyclic, we end up talking about things that you don't know yet, possibly, because we haven't gotten there yet. But at the same time, you can understand it at a high level enough to appreciate it. So why do I go into that? Well, we haven't even looked at time series problems yet, but they're very time dependent. You have to keep the data in a specific order, where with basically classification and continuous problems like regression problems, we don't have to keep the data in a specific order. But time series really depends on the data being in a specific order. So, and it also has, sorry, I got distracted. It has specific characteristics where it can be cyclic, or it can be, in other words, based on seasons or times of year or times of week. And so you've got to maintain that order of data. So k-fold cross-validation, all of that doesn't make as much sense. However, it gives opportunity where we can do linear interpolation or fancier versions of that, like cubic spline, to fill in missing values, because we can see there's still some pattern. And if the values go missing in between other values, we can just do a cubic spline. You haven't learned that yet, but it's a fancy technique to smoothly fill in missing data points. We can do linear interpolation. And we can do all sorts of other things actually easier because of the time dependency of the data. But again, you may be, we get this question a lot when I'm presenting this in a higher level, like we did last night in Indonesia. It was Lewis and Tina and I. You know, when do you know which of these to use for each type? It will become apparent because you've done good EDA, because you've gotten to know the data. And then, yes.
Yes, there is a question from Avinash, and also I think Yogo has a question.
Okay.
But before moving, I think Avinash's question is important to answer it here. What is the advised percentage of missing values to drop the rows if there is a missing values, in case of missing values?
So this question really most matters when we get to machine learning. And it will depend, once you go into machine learning, you don't want to have any missing values, Avinash. You understand? You don't go into machine learning with any missing values. So it would only be those rows you had no hope of filling in the missing values by some imputation method. But up here with the deletion, we're talking about just when we're doing correlation analysis in our early exploratory data analysis. Does that help a little, Avinash?
I think also we have to get Yogo question.
Yes. So I think Avinash is typing his response to my response. And Hugo, going ahead. Oh, wait a minute.
Okay,
Hugo,
then,
sorry. Sorry,
okay,
Hugo.
okay.
Sorry, hang on. Exactly. We retain as much data as possible, Avinash, while we're doing exploratory data analysis. And then we try to fill in missing values when we do the imputation phase. But there may be certain fields that cannot get predicted. But Avinash, I'd say the cases where we're going to, how do I put this? There's a good chance you can save more rows than you can columns. In other words, if you have a whole column that's missing data, a lot like more than 67% of the data, more than 2/3 of the data, that can be very hard to recover from, depending on your greater amount of data. So you do everything you can to make a reliable prediction to fill in that column. But also, Avinash, think about it this way. If for the data I have on hand, I find that that feature has almost no correlation to the labels, goodbye. You weren't important anyway. And so we're almost happier to find that a variable or a feature with a lot of missing data wasn't important anyway. But if we found that it was really important and there were a lot of valuables missing, we can continue with the modeling, but we also need to report this variable had a lot of missing values and that was a travesty. Here's how we adjusted for that. But that's not as good as having the actual data. And that's another opportunity to get up out of your chair, go talk to the greater organization and say, we have to fix this. We need more data for this. We can't have missing values for this. And sometimes that's as simple as talking to your data engineer and saying, can you please recode the SQL, or maybe it's the data scientist sometimes. Can you recode the SQL so that they cannot make this entire record entry, this case entry, until they've filled out all these values? Because sometimes it's okay in the programming, that is, for a value to go null. But if our analysis is saying we need that variable, then we go tell the people programming the data entry, insist that that data gets entered. Does that make sense, Avinash? You can do this or this. Okay, good. Now, okay, let me read your stuff too. Do you mean correlation? Yes. Yes. Which, about correlation, yes. But what if the feature set is important from the business? Is it okay? Again, we do the best we can. If it's important to the business perspective, we don't drop it. We do the best thing we can to fill it, but it may be that it was just too ugly and we need to go get more data.
I just want to comment here about this last message from Avinash. Now we are talking about that we have a feature and with a lot of missing data, and it's important for the, let's say, the business nature or the task nature. In this way, yes, the data collection, it has to be modified. We have to do something on the data collection level. We have to face that, okay, this is very important for you, but you didn't provide these values. How it's important. So yes, here we are trying, we don't want to be in the deadlock, let's say, deadlock situation that it's important, but it's missing. Now, which one it will be start with? Who will move it? Who will move it is the business expert or the stakeholders, or the data engineer might do something for doing that. If it's very important, we cannot move without it. Now, this is kind of business management or project management more than technical management. We cannot predict something very important. We cannot go and predict it only and then build another prediction according to predicted value. So I think we are doing a huge mistake in this way. Tom, you are on mute.
Thank you. Part of our acyclic process, Avinash and everyone, is we're doing an acyclic process through the different mechanisms of the machine learning development. But there's another dimension, getting up and going to talk to people. We can't let this value go missing in the future. Hey, this data came in dirty as a string instead of an integer. Can you make sure it's only entered as an integer? Okay, yeah. Now, it doesn't mean we throw away and wait for the clean data. We don't throw away the dirty data and wait for the clean data. We do the best we can with it. But Avinash, there could be a case where we go ahead and do the modeling, but we report we had to impute way too many values here for this variable, and that makes this less reliable. We're just being honest with you about that. We're eager to get more data for this variable so we can predict more accurately. And again, this is communication to the greater organization, but some prediction is better than no prediction in my experience. Does that help? Excellent. Yeah, it's an ongoing thing to think about. And these questions will help us write the book a lot better. Okay, some really good references. And of course, these will be available to you. And then Hugo Chukwu, what was your question?
Dad. Okay, I think you touched a bit on it when you were answering Avinash. So, but for me, I remember, and this is one of the reasons I seriously run away from reading machine learning content on LinkedIn as much as I can, because sometimes the bashing is crazy, and so scikit-learn released a part of their documentation for their library, and it had things like thresholds to say, for example, if your features, if the observations you have for your features are less than this, you should use these, methodology and stuff like that. And people started attacking scikit for that because they feel that something about that at this stage of life, we shouldn't be talking about thresholds. you know, and stuff like that. So it was a little worrisome for me. And I've heard actually my statistics teacher those days would tell us that the R squared can only be as reliable as the number of observations that you have. So if, for example, we have a piece of data that has about 60,000 observations and maybe 30,000 of them have missing values, automatically it reduces the reliability of whatever R squared we are going to predict. So for him, he believes that if any feature cannot be filled with reasonable degree of accuracy, like straight from the observation points, from the maybe from the respondents who are responding to the survey, or from the machines that are giving out the data or something, that we should just drop the feature completely. Because if you, for example, there was one we were trying to assess one time, we could only get about 100 data points or something. And out of the 100 data points, there was one variable, one feature that didn't give us, that we had just about 50 or so percent of respondents giving us responses on that. So we tried looking at the R squared. And what he said was that the R squared is going to be unreliable because we just have 50 observations. That if we had 100 observations, then we can now, you know, but if the feature, and again, another thing he said was that the importance of the feature can be explained by two things. Number one, the concurrence of a subject matter expert, and number two, the R squared. You know, like he used to tell us, then the R squared shows how responsible a feature is, you know, to the or how I'm trying to remember his exact words, but it sounds like the R squared is a way to know how much reliance, exactly that's his word, how much reliance, or how much of this variable is explained by, you know, this other feature that, okay, let me put it this way, how much of Y is explained by this X we are looking at. So he says when we have an R squared, when we look at each of the variables using whatever, maybe multinomial regression method or something, and we see the coefficients, you know, it's like him saying that because this feature that we are looking at that has, you know, incomplete incomplete responses, is looking like the subject matter expert is saying that this feature is important, but based on the few R responses we have tried to read from the correlation analysis we just did, it looks like this stuff is not important because it just has maybe like 0.1 or 0.2 stuff like that. So that's where my confusion now comes in, because some people would say drop that feature completely, or that the subject matter experts would say, no, this feature is important. So who do we believe? Do we believe the subject matter expert who says this feature is important, and then against what the correlation analysis is giving us that shows that this variable contributes up to like 70% or 80% of the explanation in the other dependent variable? So that has been my confusion all the while. I don't know if I explained this very well.
No, you did. And I appreciate it. And it really ties in well with what Avinash was asking us too. I'm a big Tony Stark fan, where he says, is it too much to ask for both? So you go. It's numbers. It's cheap computing now. Do it both ways and be honest with what you've done. But remember, we're dealing with the current sample and we're trying to improve the source that's feeding us that sample. My house is on a well. Our old filter is giving out. We bought a new system. We're going to have it installed. The water coming in could be a better quality now. We're going to put something in place, but we still have to drink. So we do our best until we get the new system installed. It's that spirit. Do it both ways and compare and learn. And don't always, again, you just do the best you can. Yes, Sometimes you have to drop an entire feature because it has too much missing data for that given sample. But if you've also verified that for that little bit of data, it wasn't a very strong correlation, you can feel better about dropping it. We listen to the domain experts, but they're not always right. When we see the data, we can show them, hey, you thought there'd be a strong correlation between these two, but there wasn't. We have a lot of missing values for this. So I will try to impute the values and do a pipeline with that, but I'll do a pipeline without this feature too, and we'll just compare them. And but for the last way I want to answer that, I'd like to end the recording because I'm going to be Tom hair down and I don't want it on YouTube. So guys, if you could end the recording.